state such a Newton's second law, actually Newton's second law for an arbitrary infinitesimally small particle of a viscous fluid moving with velocity u is an equation describing in differential form the transfer of momentum by this particle. In its most general form, this transfer is determined by the following relations. Here I just want to stress that this equation, perhaps is not perhaps exactly the central equation in hydrodynamics. Sometimes it's named Navier-Stokes equation, sometimes it's named momentum equation, just momentum of force. And so actually this is a very important equation. So it was to write it down, and so let's write. Okay. Oh. It's not removed. Oh. Oh. Okay. Some force is needed. Second law. Yeah. Professor has no force. He invented all his forces in Newton's second law of the forces, perhaps maybe some most important. So here there is also important, and we are looking for the force balance. And this force balance is actually we can use different forces. Of course, first of all, we try to use the forces which has hydrodynamic nature. And so let's write it down. So there is a raw density on the first place. Then we have partial derivatives of velocity. Velocity vector, important that it's vector, with partial derivatives in t. Then we have the part of the full derivatives. If we consider the movement, then we have this vector u multiplied by gradient, and always this acting again on vector u. So this is the transfer, but direct transfer, not like a viscosity. Okay, thanks. Okay, now it's going blue, because actually we are considering the liquid, and it's usually not dark, but it's blue. So now it's equal. So this is the force, which is actually acceleration force. In the Newton's second law, it's just all this term we can relate as ma. Oh, sorry. Multiplied it, mass multiplied it by acceleration. So all this first term is working like that. So then we can add different forces. For example, of course, one force we already considered, so we put it on the first floor, first place. Okay, you know that force? Is it? It's cosity, exactly. And then there are another forces. At the moment, we will not specify them, but they could be quite different. For example, if you are fond of the magnetic field, it will be the Lorentz force. If you are fond of the source of the convection, it will be the field of the acceleration, the binary, which, and so on. There are a vast amount of them. In some complicated cases, if there are impurities, so we have very many of them. And of course, it also could be another forces. But for us, the most important thing which we separate out of this force This is sort of the general force. But there is one force which is still also important, and it should be mentioned directly, because this is related with the hydrodynamics and sorry, with thermodynamics. No, not hydrodynamics, with thermodynamics. And you know this force. What is that? Huh? Pressure. Yeah, pressure gradient. Gradient of pressure. So if we operate more or less simple stuff, we still without thermodynamic variation, we only without pressure. But if we go to the more realistic and complicated cases, we should have temperature and so on, variation of density and so on. So let me stress again about this very important formula. I even tried it. There is a density multiplied by partial derivative of u and by time, and also usually this term is named Rossby, and it's actually the major sources of all turbulence and so on, and also it's source of the nonlinearity. So if the problems where the nonlinearity is important, it's played uncentral. But I revealed you some small secret that actually in our field, which we are working for, this term could be very small. So there is a great advantage. It simplifies the problem a lot. And we can find even almost exact solution for some problems which are shown later. So again, I just remind that rho is the fluid density, F nu, this is positive force, directly dependent on changes in the velocity of the fluid. F is external non-viscous fluid particle, and P is standard. I don't know when this equation was actually derived, but because it's named Navier-Stokes, so actually this person which was in the last century, only before the last century, because as far as my recollection, in the beginning of the previous century, it already was Busse's solution. So maybe 200 years ago, something like that. And it's still working perfectly. So the so that the I already told you, this is unique term in some part, which is related to the, if we made some analogy with Newton's law, so it's related like the product of mass and acceleration. And another name for this term, this altogether, is the total or substantial derivative of velocity. And closed in square brackets here, this is total derivative of velocity. Describe the acceleration of an infinitely small fluid particle. So actually we can use standard rules for differentiation a complex function in its useful to present with derivatives in an initial Cartesian coordinate system. So we just can use the standard rule for differentiation of complex function, and we get this term which is here in square brackets. Okay, now you see how it works. So it's what we are actually doing. We are first how to take this, somebody call it substantial derivatives, somebody call it full derivatives. Yeah. So, okay, let's call it substantial. I don't know why I call that.
because water is substantial. So now we have du vector u, which in fact is dependent on time, x coordinate, y coordinate, Cartesian coordinate, and z. And also it's fully full derivatives in time. And now we proceed as a complex function. First we divided by ordinary, getting the ordinary derivatives, just taking the first two, so it will be du by t. Then we proceed further. We take derivatives of x, and this derivative of x is also dependent on time somehow. And again, by definition, if we make this derivative of x with t, we are receiving the x component of the field. So we have du vector by dx partial derivative. And now we derive x itself. It now will be straight derivative. Just for the fun, I may get
just to have some small difference, let's do it in a little bit another notation. So we just, here we should have direct derivatives of x by dt, and often it's just denoted by the point on the x. So now we have x component. Then of course the next is coming, so we have du by dy and y with point. So now you understand that the point means derivatives by t, direct derivatives, not partial. Then the next one, du by dz, and again z with point. Okay, and now you see that you can just equal x is du x, y is du y plus, oh sorry, plus, why I wrote a plus. Oh, maybe we even do that such way. So it could be replaced by that. And this could be replaced. And so straightly not writing this lengthy formula, we see that it's just by definition this term. Because here in Cartesian system we have all these components which appear in the proper position. So this is the formula 1.8 and this formula 1.7. So we have such a result. So if the viscous force F nu is equal naught, if the viscous force is equal naught, okay, no, not yet. Then equation 7 will be an equation for an ideal non-viscous or dry fluid known as the Euler fluid, Euler equation. So this is important to mention that this ideal fluid is dry. It sounds like like nonsense, because how fluid could be dry. But in this sense that it's not how viscosity, it's common thing that it called dry. But of course it's not dry. But nevertheless, so it constitutes the L equation. This equation contains, oh sorry. This equation contains derivatives of velocity not higher than the first order, so it's important, so it's actually linear. That is why the flow of an ideal fluid is fundamentally different from the flow of a real fluid, which are determined by the viscous force F with F nu. Containing second partial derivatives of velocity. Thus, a real fluid is described by equation of a higher order than an ideal fluid, which determines a huge variety of complex phenomena, most of which have not yet been fully studied. So there is a principal difference between the L equation, which is actually linear because it not includes the non-linear term, and also with the full system, which includes the viscosity. Viscosity, very important term because it has producing the highest derivatives of the system. So sometimes even when viscosity is small in any relative units, it's impossible to remove this viscosity. And also I show in this course that namely this viscosity determines even when it is extremely small. Even this viscosity can determine the flow and all the picture of this flow. So, but another disadvantage of the Euler equation is that it's, as I already told, can make some sort of the breaks between different stuff, because there is not smooth translation, because viscosity is even on the small distance could give you the smooth transversity, but sometimes people working in this dry ideal hydrodynamic, there are also some results there, but they basically a bit artificial. So the leading term in the currently accepted approximation for the viscous force F nu was first proposed by the Navia, and there is, we have dates. So this was proposed by the Navia. So we are speaking about this equation in 1827. 1827. So it's about 200 years ago. It's about 200 years ago. Together with equation 7, this equation 7 which you saw. So actually Navier invented it in 1827. But in 1845, Stokes considered the motion of tea leaves when stirring a cup of tea with a spoon. So he was fond of tea. So he just stirred the cup with a spoon with the tea and wrote down the equation and viscosity force in the modern form. So he wrote this equation. Okay. This is the modern form of viscosity term. And Stokes wrote it like that. Nu vector. Oh, I forget here to put the vector, sorry. That's quite usual form, and it constitutes two viscosity coefficients. One of them is related to the Laplacian of the velocity, and another is related to the gradient of the divergence. So it's formula 1. We also will speak about this lambda term and gradient term. And this term is here. There is it can operate. This operator can operate like we have derivatives in all the three coordinates, and we multiply by these derivatives as a scalar field on the velocity. So we can just operate with this null operation in such a way. And here we have a divergency, and here there is a gradient of the divergency. And basically, of course, it's not our case, because the divergency is rather small in the planets. So, of course, there is some, but it's rather small, and usually, most often, it's neglected by them. But, of course, there are some situations where divergence is important. But in any situation, this Laplacian term is important. It's always on top, and it's always determines the property of the fluid. Of course, there are some situations, especially in the sun, by the way, where divergence is very important. It's because, for example, on the sun, there is same variation in 7 orders of the density. So divergence becomes quite important. Since the end of the 19th century, equation 7 with viscous force 9, equation 7 with viscous force 9, I think that you remember by heart now equation 7. I show you it's many times, so you know it's for sure. So has been cited as the Navier-Stokes equation. So this from the 19th century, it's named like that. So there is some not so good things in the developed history, because Navier invented this equation actually, or all the main ingredient of this equation, in 1827, and only after that, in 18 years, Stokes invented actually the same, and he divided this honor of the invention with Navier. But okay, now everybody knows this equation as Navier-Stokes, not just Navier. Because Navier was not so active and Stokes was very active. And sometimes people in this ancient time getting some result and was not in a hurry to publish this. They just kept it and many times passed it, and there are many laws which was not granted to the society. Sometimes even these people think that why I will give such a wonderful law to the people. Maybe still there is some who keeping this secret. So in this case, the first dynamic viscosity coefficient nu. This first dynamic. Okay, I can show by mouse. This first viscosity coefficient nu. And the second dynamic viscosity coefficient, so it has special name, the dynamic viscosity coefficient zeta, are constant everywhere in 9. So the simplest form, of course, is this Navier-Stokes equation, that the viscosity is constant everywhere, first and the second viscosity. Most stringent expression for the viscous forces, taking into account both volumetric and all the possible changes in viscosity, can be obtained by differentiating the corresponding component of the shear stress tensor and using all possible symmetry conditions. We should stress that this shear stress, which we considered in the previous lecture, is actually not vector, it's tensor, because it has two components. For example, x y, so you can have much more components. So it actually has 9 components. So it's more complicated things, and of course it can change. So generally speaking, this viscosity we can determine almost near each stress term, but it's maybe overworking sides of the problems, because actually it's very good, especially in considering this stuff which we considering here. It's impossible. It's possible to manage with the viscosity which is constant everywhere. It's a rather good approximation. While of course there are some who is opposing that as well. So more stringent expression for viscosity force, taking into account both volumetric and other possible changes in viscosity, as I solved, it's possible to determine from the variation of the stress tensor. The definition of one of the component of this tensor is given for the Cartesian coordinate system in Formula 1 above. Formula 1 above. No. This Formula 1 is actually the formula which relates the viscosity gradient of the velocity, not gradient, derivatives of the velocity in R. So actually we can determine the stress in such a way. So however, actually Cartesian coordinate system and Formula above and the others are discussed in the solution to the problem 1.4.1 below. Actually, so to this definition, I'm addressing you to the problem which will finalize this chapter. However, for the vast majority of practical applications, the simple expression 9 is quite sufficient. Simple, it means that all this viscosity coefficient maybe in the worst case depend only on radius, spherical radius, but not depend. There is no other coefficient which could be appear in a more complicated situation, and we think that we will not work with such a complicated situation, and because even with such an accuracy, this viscosity coefficient is very poorly known. So we can manage with the constant viscosity coefficient. So the complete hydrodynamic system of equation, of course, there is a main equation, which is Navier-Stokes equation, but should be another equation. It's just one. And the complete hydrodynamic system of equation, in addition to the Navier-Stokes equation, bingo, equation 7 and 9 also contains an equation for mass transfer. Here we consider transfer of momentum, and there is equation which considers direct mass transfer or conservation of the matter, which is widely known as the standard continuity equation in the form. Yeah, you see here, I will write down it. Okay, I will write down it like here just to keep the space. So we have partial derivatives of the density on time plus divergence of density multiplied by velocity vector, and all of this is equal 0. So it's 110. The system for the transfer of momentum and mass from the first scalar equation 7 and 9 and 10 for three components of the velocity vector U and scaling pressure P is completely closed by the no-slip condition for the fluid at solid boundaries. This no-slip condition is, again, is very simple. Actually, it will be added to this equation. I wrote it here, so it's very simple. So, but we should stress that it's exactly on the boundary, and this boundary rotate together with all the body, so it just equals 0. So it's 111. So it's necessary to stress that the value for the value of 3 component of the velocity vector is considered here on a solid or rigid surface in a coordinate system associated with that surface. Of course, if we consider another coordinate system, for example, when one boundary is rotated, another not rotated, so we should have involved another condition, which are related to the rotation of this. But nevertheless, in coordinate system, which is connected, linked to this, so sometimes we have the cases when we should stay in one coordinate system at one boundary and another coordinate system at another boundary. So we should make to apply in one, eventually we should have one system. So we should rearrange from one boundary to another boundary to get the proper boundary condition. And boundary condition actually finalize this problem, because actually the boundary condition is the main things which is give us possibility to choose the right solution. And if we restrict ourselves entirely to the hydrodynamic approximation, then from the point of view of thermodynamics, the density rho should be defined as a function of the pressure P. So this system has 2 thermodynamic variables, the pressure and density. So since the density variation are small in the course of the planets considered here, for example, no connection. Okay. So since the density variation are small in the course of the planet considered here, for example, less than 10% in liquid core of the Earth, then in the roughest or initial approximation, the simplest definition is rho is equal constant. It's completely justified, stating the constancy of density everywhere. In this case, the continuity equation is simplified to the widely known incompressible equation, divergence of U is equal naught, and in 9 the second velocity can be discarded. So actually, did I write that? No. Okay, it was to wrote, it's not wrote here in the presentation. But this formula, while it is not the number, but nevertheless it's a rather important formula. If we consider the particular case of this situation, when rho is constant, then from that we have, let it put it this way, in that case we have, you see that if rho is constant, then we have the 0 here, and if rho is constant, it's actually could be going from these brackets, and eventually we have divergence of U is equal 0. And it's a very important case, which is basically explored in all approximation. However, this case is somehow also important, but also could be some small variation of the density. And if we have this small variation, we can take them into account in the linear approximation, and it could be the base of the convection, which you consider later. So in this case, it's finally, let's finalize this chapter with a completely known force F and constant density rho. We obtain a system for four-scalar equation for determining the pressure and three component of the velocity vector based on corresponding boundary condition 11. So actually, we may write down the final system. There is still place here. So boundary condition 11 we should mention again. This boundary condition, again, I stress that it's in the coordinate system which rotate with the boundary. And if the boundary rotates with different, so it will be some difference. But eventually we write down the important case of the system which we will consider further in the following chapters. And so it's constitute all the equation which we need for to solve the problem. And this is, of course, first of all, Navier-Stokes equation du by dt plus u, so, and equal. So in this case also dynamical part of the viscosity vanished. So in this case we can write down here only general part of the viscosity. Dynamical viscosity is omitted because the divergence is equal not. And so here we will have like that. And then we have all other forces here, then the minus gradient P, and we divide everything on the density. And there is still divergence of the velocity field equals 0. So this is equation 112. Okay. Okay. It seems we finished this chapter. So the next chapter will be rotating coordinate system. Okay, so maybe we can stop. Yeah, please ask the question, if any.
Equation 1.9.
1.9?
Yeah.
This?
Yeah. So that equation is applicable only to Newtonian fluid, right? Because it doesn't hold for non-Newtonian. And the relationship between stress and strain rate is non-linear.
Yeah, it's Newtonian fluid. It's applicable only to Newtonian.
So when you deal with interior of, let's say, stars where the fluid is plasma, it doesn't apply.
Yeah. In some approximation, of course, it's possible to apply. But in some cases, of course, it also cannot apply. But in this case, of course, we should consider some addition which could be replaced with this stuff. One more question?
Okay. It's fully hearing. I mean,
So you mentioned that this method estimation can be applied so this non-divergence condition for the loss can be applied for example, when the convection in the sun. But as far as I know, we need a lot of models that apply over some line of they use the Busse approximation and they work on theory why we use so this non-divergence condition is applied for the model and for time.
Unfortunately, this non-divergent, of course, it's not because they are rarely applied, because it's much easier to use the non-divergent conditions than divergent conditions. So the people are actually making the solar approximation. They're using viscosity, they're using that it's non-divergent, and so it's they are looking at the place where is the light. there is no light. The situation is of course very, very complicated, especially because there is a huge variation in the density. So actually, in its whole, the sufficient difference is that usually people are writing the equation as a temperature equation, but in this case it's necessary to go to the entropy equation. And there are some books which are doing so, but nevertheless it's a rather complicated problem, and frankly speaking, in some there is still no proper solution that will describe everything in accordance with the real situation. There is only approximation which not sometimes, but almost all the time are very good. But unfortunately, it's difficult to do. So, the real situation is much more simple, so we can approximate this Busse stuff. And even for the Earth, there is some doubt that it's applicable. So again, we should use this almost adiabatic approximation, which we, for example, used with you.
There is also an elastic.
Yeah. Is there very more questions?
These are approximations. If we assume many things, how we can correlate them with the observations and the experiments?
You mean this approximation?
These equations, we have so many assumptions.
Yeah.
Approximations.
Yeah.
How we can correlate them with the experiments and the observations?
We can correlate this with the experiment because the experiments which are come and deal with rotating spheres and some gap between them. Our accumulator survey, some of them are shown to you. So we can make some direct experiment which is possible to compare with this theory. And also there is of course some model which can test the Earth's interior and to find at least to estimate what the conditions there, and we all and in this case maybe the situation in Earth is better.
In the terms that we can more precisely and with less errors to approximate the system in the Earth, while in Sun the situation is much more complicated. It's quite difficult, namely because this term, this nonlinear term, in Sun is playing crucial role. But in the situation with Earth, this term has a very minor role, so we can work in such a situation when this main nonlinearity is not so more important And so it's possible by some methods to model the planetary situation and the Earth, of course, situation to much more accuracy than for the Sun, if compared with Sun, and stars, of course.
From where that the turbulence is coming, turbulence is given by which terms?
Turbulence is given directly by this source. It's okay. This source is all the source of the problem. It's non-linearity, and turbulence also coming from here, because usually people name it even a Reynolds stress term. So it's exactly from here turbulence is going. And of course, the simplest estimation of the turbulence, if we compare this term and this viscosity term, you see that if you just take this u, and because here there is a derivatives, if you take this u and
some characteristic size, you can directly have the estimation of the turbulence. You just take the velocity average, multiply it by the typical distance, and in the order of magnitude, you obtain turbulence viscosity. So it's directly come from this term.
Non-linear term. But in the Earth, we are considering this is negligible. In the Earth, in the modeling of the dynamo models, if we for the Earth, if we consider that term as a negligible effect, very small, then how to model the turbulence?
You mean viscosity has negligible effect?
No, non-linear term.
It depends actually. If we consider the situation of Earth, it has almost negligible effect. But in the case of the Sun and stars, it has very many things. Such effect.
Any questions? Then we call it as a day. Okay.
Okay, thank you. Thank you for coming.